In this lesson, we're focusing on the time value of money as it applies to a single cash flow, also known as a lump sum investment. By the end, you should be comfortable calculating the future value of one cash flow, understanding how compounding works, and seeing how different compounding frequencies affect returns. We'll also introduce the effective annual rate and finish with a look at continuous compounding. Let's start with a simple example. Imagine you deposit $1,000 into a bank account. The bank pays a fixed interest rate of 5% per year, compounded annually. After 1 year, assuming you make no withdrawals, your balance will be the original $1,000 plus 5% interest. That interest is $50, so you now have $1,050. Now suppose you leave the money in the account for a second year. This time, interest is earned not just on your original $1,000, but also on the $50 interest you earned in the first year. At the end of year 2, you earn 5% on $1,050, which is $52.50. This is compounding in action, earning interest on interest. Over long periods, compounding has a powerful effect. Even relatively small investments can grow substantially when given enough time. To generalize this relationship, we introduce a few key terms that you'll use throughout the course. Today is time zero. The amount you invest today is called the present value. The interest rate, also known as the discount rate, applies to each time period. The value of the investment at a future point in time is called the future value. The relationship between these is straightforward. The future value equals the present value multiplied by a future value factor. That factor is 1 plus the interest rate, raised to the power of the number of time periods. Now let's apply this with a slightly more involved example. Suppose Anderson expects to receive $100,000 from a bond that matures 2 years from today. Once the money is received, it will be invested in a fund earning 8% per year. The goal is to determine how much that investment will be worth 5 years from now. Before doing any calculations, it helps to draw a timeline. Timelines make time value of money problems much clearer. Today is time zero. 2 years from now is when the $100,000 is received. The value we want to find is 5 years from today. That means the money is invested for 3 years, not 5. This step is crucial. With the timeline set, we plug the values into the future value formula using a present value of $100,000, an annual rate of 8% and 3 years of investment. Doing that gives a future value of approximately $126,000. So far, we've assumed interest is compounded annually. In practice, interest is often compounded more frequently. When compounding occurs more than once per year, the quoted annual rate must be adjusted to match the compounding period. For example, if a 5% annual rate is compounded semi-annually, each period uses a rate of 2.5%, and there are 2 compounding periods per year. Using more frequent compounding results in a slightly higher future value, even though the quoted annual rate stays the same. This is a common source of mistakes on exams, especially under time pressure. So always check that the interest rate and number of periods are expressed in the same time units. This brings us to an important question. If interest is compounded more frequently, are you effectively earning a higher return? The answer is yes, and that's why we use the effective annual rate. Imagine 2 banks. One advertises a rate of 4.95% compounded monthly. Another advertises 5% compounded semi-annually. At first glance, the second rate looks better. But what really matters is how much interest you earn over a full year. The effective annual rate measures the total return earned in 1 year after accounting for compounding. To calculate it, we use the future value factor for 1 year and subtract 1. The key rule still applies. The interest rate and number of periods must use the same time unit. For monthly compounding, we divide the annual rate by 12 and use 12 periods. For semi-annual compounding, we divide the annual rate by 2 and use 2 periods. When you calculate both effective annual rates, you'll find that the account with more frequent compounding produces a slightly higher effective return, even if the quoted rate is lower. This is why effective annual rates are so useful. They allow us to compare interest rates with different compounding frequencies on an equal basis. As compounding becomes more frequent, the effective annual rate increases. That leads to a natural question. What happens if compounding occurs continuously? With continuous compounding, interest is applied an infinite number of times per year. In this case, we use a different formula involving the mathematical constant e, which is approximately 2.718. The future value under continuous compounding equals the present value multiplied by e raised to the power of the interest rate times the number of years. Let's finish with one final example. Skywalker invests $60,000 into an account that compounds continuously at a guaranteed rate of 4% per year. The plan is to leave the money invested for 6 years. The question is how much total interest is earned by the end of that period. Using the continuous compounding formula, we multiply $60,000 by e raised to the power of 0.04 times 6. This gives a future value of approximately $76,300. Subtracting the original investment shows that the total interest earned is about $16,300. This lesson introduced the foundational ideas of present value and future value for single cash flows. As you prepare for the exam, always remember to align the interest rate and number of periods to the same time unit. That one habit will help you avoid many common errors. In the next lesson, we'll reverse the process and focus on calculating the present value of a single cash flow.